What? Am I audible? Am I audible? Am I audible in form? Is there any disturbance in my voice? Yeah, we'll start the class. Lag lead compensators. The compensator which have the characteristics of lag as well as lead network is known as lag lead compensator. So, so in a lag lead network, when a sinusoidal signal is applied as input, both the phase lag as well as phase lead occurs in the output, but at a different frequency regions. Okay. So in lag lead network, if you give the sinusoidal supply, then both phase lag will occur as well as phase lead will occur in the output at different frequency regions. And phase lag occurs at usually at low frequency region, and phase lead will occur at high frequency region. So we can say that phase lag varies from lag to lead as the frequency is increasing. Okay, not phase lag, sorry. The phase angles will vary from lag to lead as frequency is increasing from 0 to infinity. Why? Because phase lag is occurring at low frequency region and phase lead is occurring at high frequency region. Therefore, phase angle omega, okay, phase angle omega will vary from lag to lead as frequency is increased from 0 to infinity. Okay. So a lead compensator basically increases the bandwidth and it will speed up the response and decreases the maximum overshoot in the step response. Okay. So if you give the step input to a lead compensator, it usually increases the bandwidth and it also speeds up the response, but it decreases the maximum overshoot. So if you consider a lag compensator, it increases the low frequency gain and hence it will improve the steady state accuracy, okay, of the system. Okay, in- it will increase the low frequency gain. Once again, lag compensator will increase, sorry, where is it? Lag compensator will increase the low frequency gain, and hence it will improve the steady state accuracy of the system, but it will reduce the speed of the response. Okay, it will reduce the speed of the response due to reduced bandwidth. Okay, so speed of the response will reduce because of the reduced bandwidth in the case of lag compensators. Now, if improvement in both transient, if you want to improve, okay, both transient as well as steady state response, then we need both lead compensator as well as lag compensator. Okay. So now to improve the transient response as well as steady state response, we require both lead compensator as well as lag compensator simultaneously. Okay, so since we require both lead compensator and lag compensator simultaneously, instead of using them separately, okay, so we can combine those two together to form a compensator which is known as lag lead compensator. Okay, so because of these advantages of lag compensator and lead compensator, they are combined together and they are operated as a single compensator. Okay, lag compensator and lead compensator, they are combined their characteristics. In order to combine their characteristics, what are the characteristics that they have? The both the transient response, okay, as well as steady state response will increase, okay, when we are using both lag compensator and lead compensator. So instead of using separate lag compensator and lead compensator, we can use a single compensator which is known as lag lead compensator, which has the all the advantages of both lag and lead compensators. Okay, so this lag lead compensator will combine the advantages of lag compensator as well as lead compensator. Okay. Now, let us see the S-plane representation of lag lead compensator. So, lag lead compensator, it poses two poles and two zeros. So, you can see on the S-plane, you can see this is 1 0, this is 1 0. This is a pole and this is a pole. Total two poles are there. Okay. Two poles are there and two zeros are there. Okay. So this the lag lead compensator which poses two poles and two zeros such that compensation will increase the order of the system by two. Okay. So it has two poles and two zeros. Therefore, the order of the system will increase. Okay, when you provide compensation to any system, the order of the system will increase by two. Okay, unless and until the poles and zeros cancel each other. Okay, if they cancel, poles and zeros are cancelled, then the order will not increase by two. But if they are not cancelling, then order of the system, since the compensator has two poles and two zeros, okay, since the compensator has two poles and two zeros, the order of the system will increase by two. So here uh, we already know that lag section has one real pole and one real zero. The pole to the right of the zero. Okay, pole will be on the right of the zero. So this is the lag section. This is our lag section. And lead section has one real pole and one real zero, but zero is to the right of the uh, pole. Okay, so this is our lead section. So this is lead. Sorry. This portion is the lead section. Okay, and this is our lag section. Able to write properly. So this is our lag section. This is our lead section. Total 2%. Two zeros will be there on the um, left half of your S plane, on the LHS side of your S plane. So the transfer function of lag lead compensator, it is given by GC of S is equal to S plus 1 by T1 into S plus 1 by T2 by S plus 1 by beta T1 into S plus 1 by alpha T2, where beta is greater than 1 and alpha lies between 0 and 1. So this is the transfer function of lag lead compensator, which has two poles and two zeros on the LHS side of your S pin. So let us realize this lag lead compensation. So next, realization of lag lead compensator using electrical method. Okay. So let us realize this lag lead compensator using the electrical network. Okay. So you can see here, it is an RC network. Okay, this is an RC network. Input is in EI of S and output is E naught of S. Okay. So there is on the series branch, there is a parallel combination of R1 and C1 capacitor. And on the parallel branch, these two elements are connected in series. Okay, R2 and 1 by C2 is C2. So we have written this capacitance values in Laplace form. Input and outputs as well as current is also in Laplace form. So if to this circuit, so this is a Laplace circuit we can say. So to this circuit, if we apply voltage division rule, okay, if we apply voltage division rule to this circuit, so what is our output voltage? Output voltage is equal to input voltage into, okay. So self impedance is, this is the self impedance, both are connected in series. Self impedance by opposite impedance plus self impedance, that is the output voltage. So that is the voltage division rule formula. So you let us see. So what is our output voltage? That is the input voltage equal R2 plus 1 by SC2 by R1 parallel with 1 by SC1 plus R2 plus 1 by SC2. Okay, R2 and 1 by SC2, they are connected in series. R1 and 1 by SC1, they are connected in parallel. So just simplify it, you will get E naught of S by EI of S is equal to S into R2 C2 plus 1 by SC2 by R1 into 1 by SC1 by R1 plus 1 by SC1 plus S into R2 C2 plus 1 by SC2. So this is very much familiar voltage division rule, simple circuit. RC circuit is there. So simply you have to write the equations, okay, which you can easily write it down. It's very easy to write. Simple circuit, nothing complicated. So just rearrange the terms. Okay. If we rearrange the terms, you will get E naught of S by EI of S is equal to SR2 C2 plus 1 by SC2 all divided by R1 by SR1 C1 plus 1 plus SR2 C2 plus 1 by SC2. Again, just take the common denominator in the denominator term. If we take the common denominator of this term, so what do you get? You will get E naught of S by E of S is equal to SR2 C2 by plus 1 by SC2 divided by SR1 C2 plus SR1 C1 plus 1 into SR2 C2 plus 1 by whole divided by SR1 C1 plus 1 SC2. So send this denominator to the numerator term, just rearrange the terms, you will get E naught of S by EA of S, SR1 C1 plus 1 into SR2 C2 plus 1 by SR1 C2 plus SR1 C1 plus 1 into SR2 C2 plus 1. Okay, so I'm simply reading the equations. You, being an engineer, you know how to simplify these terms and how to rearrange the terms. It's simple. Okay, so once again, if I rearrange the terms, if I take some terms common, so what do I get? R1 C1 R2 C2 into S plus 1 by R1 C1 into S plus 1 by R2 C2 by S R1 C2 plus R1 C1 R2 C2 into S plus 1 by R1 C1 into S plus 1 by R2 C2. Now, on dividing the numerator and denominator by some R1 C1 R2 C2, you will get E naught of X by E of S is equal to S plus 1 by R1 C1 into S plus 1 by R2 C2 all divided by S by R2 C1 plus S plus 1 by R1 C1 into S plus 1 by R2 C2. Okay. So here, by further simplification, you will get S plus 1 by R1 C1 into S plus 1 by R2 C2 whole divided by S square plus S into 1 by R1 C1 plus 1 by R2 C2 plus 1 by R2 C1 plus 1 by R1 R2 C1 C2. And the transfer function of the lag lead compensator, we already know for the lag compensator transfer function and lead compensator transfer function, we already know. So just combine those two compensator transfer functions. You will get GC of this is equal to 1 plus T1 by 1 plus S beta T1 into 1 plus S T2 by 1 plus S alpha T2. Just compare this transfer function with the above equation. So if you compare this transfer function with the above equation, by comparing what you get is T1 is equal to R1 C1, T2 is equal to R2 C2, and this R1 R2 C1 C2 is equal to alpha beta T1 T2, and 1 by R1 C1 1 by R2 C2 plus 1 by R2 C1 is equal to 1 by beta 1 plus 1 by alpha T2. Okay, simply by comparison you will get these terms. So from this equation 5. Okay, this is our equation 5. What is it? R1, R2, C1, C2 is equal to alpha, beta, uh, T1, T2. So from this, you can determine what is alpha, beta. Alpha, beta is equal to R1, R2, C1, C2 by T1. Sorry, alpha, beta is equal to, yeah, by T1, T2. Okay, just rearrange the terms. You will get this. I think I have written in the reverse direction. Okay, wonderful. So from above equation this 3, 4 and this equation 7. Okay, from all these equations, if you compare them, you will get alpha into beta is equal to 1. Okay, alpha beta is equal to 1. Now, alpha beta is equal to 1 means what is alpha? Okay, alpha is what? Alpha is, 1 second. So alpha and beta are the attenuation and gain and the amplifier values. So if you don't want them, you can simply cancel them. Okay. So by looking at this above equation, alpha beta is equal to 1, what we can say is that alpha beta are not allowed as independent choice. Okay. But if we take separate lag and separate lead network, then you can independently choose alpha value, alpha and beta. But when you can combine lag and lead compensator, when you are considering lag lead compensator, alpha beta cannot be considered independently. Okay. So the transfer function of electrical lag lead compensator, you can replace if you have okay, you can replace alpha by 1 by beta as shown below. Okay, you can replace alpha by 1 by beta. So wherever alpha was there, I have replaced it by 1 by beta. Okay, so this is it. This is the transfer function for the electrical system. Now let us go to the frequency response of lag lead compensator. So what is our compensator transfer function? S plus 1 by T1 into S plus 1 by T2 by S plus 1 by beta T1 into S plus 1 by alpha T2 is our lag lead compensator transfer function. You just simplify, you will get alpha beta into 1 plus S T1 into 1 plus S T2 by 1 plus S beta T1 into 1 plus S alpha T2 is our compensator transfer function. This is the transfer function of lag lead compensator. Now we want the frequency response, isn't it? We want the frequency response of this lag lead compensator. So since we want the frequency response of lag lead compensator, replace S by j omega. Okay, replace S by j omega. If we replace S by j omega, you will get this GC of j omega equal to alpha beta into 1 plus j omega t1 into 1 plus j omega t2 by 1 plus j omega beta t1 into 1 plus j omega alpha t2. Okay. So now if I don't want alpha and beta, if alpha beta value is 1, okay, so by some, okay, so we know one is the attenuation, one is the amplifier value. So simply multiply it with 1 by alpha beta, you'll get alpha beta will be cancelled. So let us assume alpha beta is 1. Then, okay, so if alpha beta is equal to 1, then what will happen to the transfer function? Transfer function will be dc of j omega equal to 1 plus j omega t1 into 1 plus j omega t2 by 1 plus j omega beta t1 into 1 plus j omega alpha t2. Okay, so here we have four factors in GC of j omega. What are those factors? First order numerator factor, first order numerator factor, two first order numerator factors, two first order denominator factors. Total four factors are there. So we can get four corner frequencies: omega C1, omega C2, omega C3, and omega C4. So always omega C1 will be less than omega C2, omega C2 will be less than omega C3, omega C3 will be less than omega C4. Okay, that is it. So, so yeah. Omega C1 is given by 1 by beta T1, omega C2 is 1 by T1, omega C3 is 1 by T2, omega C4 is 1 by alpha T2. So how to get it? Okay, so here you can see coefficient of omega is beta T1, coefficient of omega is alpha T2, coefficient of omega is T2, coefficient of omega is T1. So 1 by beta T1, 1 by alpha T2, 1 by omega T2. Sorry, 1 by T2, 1 by T1. That's it. That's what is written here. These are all the corner frequencies. I hope you know how to determine the corner frequencies if you have the basic factors for the Bode plot. Okay, so by analysis similar to that of your Bode plot, lag compensator and lead compensator, so we can simply sketch the Bode plot here, because first it is lag lead compensator. So you can see here up to here, this is the characteristics of a lag compensator, magnitude plot of lag. This is the characteristics of lead compensator, magnitude plot of lead. Similarly, up to here, this is the characteristics of phase plot of lag, and from here to here, this is the phase plot of lead compensator. So since it is a lag lead compensator, okay, since it is a lag lead compensator, just observe at low frequencies, the magnitude plot is similar to lag compensator, as well as phase plot is also similar to lag compensator. Okay, this is it. Magnitude plot and phase plot. This is lag compensator characteristics. Okay, lag compensator characteristics. If we observe this magnitude, this is magnitude plot of lead compensator characteristics. This is the phase plot of lead compensator. So this is lead compensator characteristics. Okay, lead compensator, magnitude plot as well as phase plot. This is the magnitude plot as well as phase plot of lag. So the combination of lag and lead compensator characteristics, both the magnitude plot and phase plot, you can see here. This is the magnitude plot, this is the phase plot. Now let us solve some numerical problems. Not some, we will solve one numerical problem on this. So all of you take a graph in your hand. Make sure you have graph in your hand. Do you have semilog graph? Do you have semilog graph? Just mention. Do you have the semilog graph with you or not? You just mention it. Mention in the chat box whether you have the similar graph sheets or not. So you will solve numerical problems on lag lead compensator, one numerical problem. So all of you take the similar graph sheet. Yeah. Keep the similar graph sheet with you and we will continue. So let us start. Write down the problem while I am explaining it. So a unity feedback system as an open loop transfer function. Okay. Unity feedback system means what? Unity feedback means H of S is equal to feedback gain. Feedback is that is H of S is equal to 1. Okay. So forward path gain G of S is given, that is K by S into S plus 3 into S plus 6. This is the forward path gain. Design a lag lead compensator to meet the following specifications. Okay. You have to design a lag lead compensator to meet the following specification. What are all the specifications that are to be met? Velocity error constant Kv equal to 80 and phase margin gamma n greater than 35 degrees. So velocity error constant should be 80 and phase margin should be greater than or equal to 35. Okay, this is it. Just write down the problem within a minute. Now let us see the solution of this problem. So step one is to calculate the gain K value. Okay, step 1 is to calculate the gain K value. So let us consider unity feedback system. Sorry, I already mentioned. We need not consider. It is given in the question. It is a unity feedback system. So it's a unity feedback system. So H of S is equal to 1. H of S is equal to 1. And we already know the formula Kv velocity error constant Kv is equal to limit S tends to 0 S G of S H of S. Okay, limit S tends to 0. Limit S tends to 0 S G of S H of S. Okay, this is the formula. But since it is a unity feedback system, H of S is equal to 1. No need to write this H of S. If you want, you can write and later you can just write it down. So Kv equal to limit S tends to 0, yes, G of S, H of S. And in the question itself, they have given velocity error constant. It should be equal to 80. Kv is 80. So just write it down. If you complete, just mention you have completed. Okay, then let us proceed further. Now, kv is equal to what? Limit s tends to 0, yes, g of s. What is g of s? K by s into s plus 3 into s plus 6. Now here already s is there, so this s and this s they will cancel. And now substitute the limit. If we substitute the limit, this s will become 0 and this s will become 0. So what is left? Okay, this s will become 0 and this s will also become 0. After this numerator s and denominator s cancel, substitute the limit. If you substitute the limit, both the s will become 0. What is left over? K, 3 and 6. So k divided by 3 into 6, you will get. So what is kv value? It is mentioned in the question 80. 80 is equal to k by 3 into 6. So just rearrange the terms and determine k value. So k is equal to 80 into 3 into 6. K is equal to 1140. Write it down. K is equal to 1140. You just write, and as soon as you complete, just mention that you have completed. Okay, then now let us take our open loop transfer function, that is g of s. I'll take the laser. So g of s is equal to what? Instead of k, right? 1140 by s into s plus 3 into s plus 6. Now here it is not in the form of 1 plus st form. It just convert all the factors in 1 plus st form. So in order to convert that, take 3 common here and 6 common here, and you will get s into 3 into 1 plus s by 3 plus 6 into 1 plus 1 plus s by 6. So we want to convert those terms in basic factor form. So basic factors, in order to convert those terms in the form of basic factors. So we have taken 3 common and 6 common. So when you take 3 common, 6 common, what do you get? You will get you just uh, s into 3 plus 1 by s3 plus into 6 into 1 plus s by 6 you will get. And you just simplify this, you will get 80 by s into 1 plus 0.33 s into 1 plus 0.167 s. Okay, so this is what is our open loop transfer function now. Okay, in S domain, we have got the open loop transfer function in S domain. Now let us convert that open loop transfer function which is in S domain into sinusoidal transfer function. Now to convert the open loop transfer function which is in S domain form into sinusoidal transfer function, just replace S by j omega. Okay, replace S by j omega. So what will happen to open loop transfer function g of S? It will become g of j omega equal to 80 by j omega into 1 plus 0.23 j omega into 1 plus 0.167 j omega. So this is our open loop transfer function, which is sinusoidal in nature. Okay, sinusoidal open loop transfer function. Sinusoidal transfer function, simply you can say. Just write down all the equations as quickly as possible. You complete, just mention. So if you observe here, yeah, if you observe here, there is one integral factor. Okay, one integral factor, one first order denominator factor, and one more first order denominator factor. So there are two first order denominator factors. So since there are two first order denominator factors, so how many corner frequencies do we get? We will get two corner frequencies. Okay, we will get two omega c values. Okay, omega c, you will get two values. We will get two omega c values. Why? Because we have two first order denominator factors. So let us go for the magnitude plot. Omega c formula is what? 1 by t. So omega c1 equal to 1 by, what is our t value here? 0.33, one value, another t value is 0.167. Okay, t value 1 is 0.33, another t value is 0.167. So first corner frequency 1 by 0.33, another corner frequency 1 by 0.167. So you just simplify it. Omega c1 is 3 radians per second and omega c2 is 6 radians per second you will get. Okay, omega c1 3 radians per second and omega c2 you will get 6 radians per second. Okay, so now let us draw this table 1. So write down all the basic factors. You have one integral factor, one first order denominator factor, and one more first order denominator factor. Write all three factors in the first column. Write all three factors in the first column. So now write down the corner frequencies of these factors. Integral factor will not have any corner frequency. Okay. So for this first order denominator factor, corner frequency we have already calculated. Omega c1 equal to 1 by t. What is t here? 0.33 is our t. So 1 by 0.33 will get 3 radians per second. And under corner frequency for this second factor, first order denominator factor, that is t value is 0.167. So 1 by 0.167 you will get 6 radians per second. So these two are corner frequencies. This is our second column. Now let us see the slope of each factor. See, we know integral factor slope is minus 20 and slope of your first order denominator factor is minus 20. Slope of first order denominator factor is also minus 20. Okay. So for first factor, there will not be any change in the slope. So write down the slope of first factor in the second row and add it with the slope of that particular row factor. So minus 20 you will get minus 40. Now send this minus 40 to the next row and add that minus 40 with the slope of that particular row factor. So minus 40 minus 20 you will get minus 60. Okay. So always remember for first factor there will not be any change in slope. So first factor slope you write it in the next column or next row and add it with the slope of that particular row factor and whatever change in slope that you get in that particular row, send it to the next row and add it with the slope of that particular factor. Okay, that's it. So we have got change in slopes of minus 40 and minus 60. So draw the table quickly and write it down. Okay, I hope you have completed. So let us proceed. Now, of course, we have two corner frequencies. Let us consider two more frequencies. One is low frequency, another one is high frequency. Okay, so let us consider two more frequencies. One is low frequency, another one is high frequency. Low frequency is omega L, high frequency is omega H. Okay, so low frequency is omega L, high frequency is omega H. So omega L should be chosen in such a way that omega L should be chosen in such a way that omega L is less than omega C, and omega H should be chosen in such a way that omega H is greater than omega C. Okay, so here of course we have two corner frequencies. Therefore, omega L should be chosen. One second. Omega L should be chosen in such a way that it is less than omega C1. Omega H should be chosen in such a way that it is greater than omega C2. Okay. So here you can see omega C1 is 3. Omega C1 is 3. Omega C1 is 3. Omega C2 is 6. So omega C1 is less than omega C2 here. Okay. So omega C1 since it is less than omega C2. So omega L should be less than omega C1 and omega H should be greater than omega C2. Okay. So this is it. So let us choose omega's L some value less than omega C1. So omega C1 was 3. So omega L I have chosen 0.5 which is less than 3. Omega C2 was 6. Omega H I have chosen 20 radians per second which is greater than omega C2. Write it down. Okay. So in total, how many frequencies values that do we have? We have omega L. We have omega L value now. Okay. We have omega H value. We have omega C1 value. We have omega C2 value. Total 4 frequencies are there. Omega L, omega C1, omega C2, and omega H. For all these omega values, let us determine the magnitude A. Okay, A in decibels. Okay, so A is magnitude of G of j omega in decibels. Okay, magnitude of G of j omega in decibels is denoted by A. So let us determine A. So here I didn't change this. So total omega L, omega C1, omega C2, and omega H, total 4 frequencies. So for omega equal to omega L, what is A? 20 log of 80 by omega. So 20 log of 80 by omega, what is our omega value? Omega value is 0.5. So here, this is 80. 80 by 0.5, you just solve it. You will get 44 decibels. Just write it down. Just write it down. So I hope you have completed. Now let us consider omega equal to omega c1. Omega equal to omega c1. So A is equal to 20 log of 80 by omega. What is omega value now? C1 value. C1 value is 3. So 20 log of 80 by 3. Just solve it, you will get 28.5 decibels, which is approximately, you can write either 29 or 28, yeah, which it doesn't matter. Okay. So it is usually, for you get any 0.5 value, you should upgrade it to higher value. Here I have written 28 decibels. You need not write 28, you can write 29 decibels. So when omega equal to omega c1, which is omega c1 is 3, when you substitute that in your formula 20 log 80 by omega, you will get 28.5, which is approximately, actually you can write 29 or 28, doesn't matter. Okay, next let us consider omega equal to omega c2. Omega c2 value is 6. So after first corner frequency, this is the formula that you have to use. A is equal to slope from omega c1 to c2 into log omega c2 by c1 plus A at omega equal to omega c1. Okay. So what is the slope from omega c1 to c2? For that, go to the table. Slope from omega c1 to c2. So this is our table. This is our omega c1. This is our omega c2. What is the slope from omega c1 to c2? It is minus 40, isn't it? Slope from omega c1 to omega c2 is what? Minus 40. So here it is minus 40 into log of what? Omega c2. Omega c2 value is what? It is, I think here, omega c2 is 6 and omega c1 is 3. So here I should change it. This is 6. This is 3. It's not changing. Okay, so log of 6 by 3 plus, what is A at omega equal to omega c1? A value at omega equal to omega c1 is 28 decibels. So 28. So just solve it, you will get 16 decibels. Okay, just write it down. We complete inform so that I can proceed. Okay, then let us consider omega equal to omega h. Omega equal to omega h. Omega h value, what did we assume? 20. Now, what is the slope from omega C2? So the formula for to determine A value is A equal to slope from omega C2 to omega H into log of omega H by omega C2 plus A at omega equal to omega C2. So now let us see what is the slope from omega C2 to omega H. Omega C2 to omega H. So what is our in this table? In this table, this is our omega C2. What is the slope? Minus 60. So omega H is greater than omega C2. So this minus 60 will go to omega H. So slope from omega C2 to omega H is minus 60. So that's what I have written here, minus 60 into log of omega H value is 20 by omega C2 is 66 plus 16. What is this 16? It is A at omega equal to omega C2. So A at omega equal to omega C2, what is the A value? A value is 16 decibels. So write down that and just solve it. You will get minus 15 decibels. Okay. Now, so you can plot the magnitude plot. Okay. So for these omega values, omega equal to omega C, omega L, omega C1, omega C2, and omega H. And you have got 4 A points, magnitudes. You have got 4 A values. Okay. So let us give some notations to those A values. A, B, C, D on similar graph is assume 1 unit equal to 10 decibels on y-axis. Okay. Consider 1 unit equal to 10 decibels on y-axis. So let us go to the magnitude plot. Okay, let us go to the magnitude plot. Or okay, so let us go to the magnitude plot. So this is it. So this is my plot. So I have considered this point x-axis 0.01. I have not written here, but this point is 0.01, this is 0.1, this is 1, this is 10. Omega in radians per second, x-axis, omega in radians per second. And what about y-axis, A in decibels? I have considered 10 decibel y-axis. Okay, there is my cursor. Y-axis 1 unit equal to 10 decibels. So I have started with 80, 70, 60, 50, and so on. So I have left here, but you can start writing 80 from here. Okay, 80, 70, 60, and so on. Okay, up to minus 60 I have written. This is my minus 60. This is my 80. Okay, so just take the scale on the graph, similar graph sheet, y-axis scale. X-axis is what? This is 0.01. Okay, this is 0.01, this is 0.1, 1, and 10 radians per second. Omega value. X-axis omega, y-axis A. Okay. Take the scale on the graph on similar graph sheet. Okay, I hope you have completed. Now, locate the points on the graph sheet. So what are my points? What are my points when omega equal to omega L? What is my omega L value? 0.5. So where is my cursor? Pointer. This is it. Yeah. So for 0.5, what is 0.5 here? This is my 0.5, isn't it? So this is 0.5 omega value, x-axis. This is 0.5. For 0.5 means I can write here 0.5. For 0.5, what is A value? A value is 44 decibels. So this is 44 decibels for 0.5. Right. This is 1 point. Next point is for omega L, it's over. Next omega is C1. Omega C1 is 3. So for omega C1, 3. 3 means, so this is 1, 2, and 3. This is my 3. Omega value is 3. Okay, for omega value 3, what is the magnitude? This is 28 decibels. This is 28. Okay, this is 28. This is my point. Okay. So listen to me. Okay, similarly, next omega value is 16. This is 10, 20. This is, sorry, omega value is not 16. Magnitude A is 16. And omega value is 6. This is 5. This is 6. Omega value next is 6. So omega value is 6. So here you can write 6. So for 6, it is 16 decibels. 16 means here, somewhere here. This is it. 6, okay. So one more point is there, omega value is 20 and A value is 16 decibels. So for 20, omega 20, omega is 20. Omega value is 20. A value is minus 15, sorry. A value is minus 15. So I will erase this, whatever I have written here. Whatever lines that I have put here, I will erase. So for omega value 20, 20 is, this is 20. This is 20. I'm able to write 20. This is 20.20 decibels, sorry, 20 radians per second. Omega value is 20 here. This point is 20. And for 20 omega, minus 15. So minus 15, this is minus 15. Okay, this is our point. So these are the points. Okay, these are the points for the magnitude plot. So just join them, you will get this. If you join them, you will get this. This is our plot. And you can even write the slopes. Okay, you can write the slopes. So slope from first point to second point. What is this change of slopes? From one point to another point. From the table A. Okay, magnitude plot table, you can write down the slopes above this. Okay, here slope change in slope values, you can write it here. Okay, this is our magnitude plot. Now let us go to the, two times I have written here. Let us go to the phase plot. So So let's go to the phase plot. So what is our sinusoidal transfer function g of j omega? You can rewrite it in magnitude and phase angle. So if you write the magnitude and phase angle of the g of j omega, magnitude is k by omega root of 1 plus omega square into 0.33 square root of 1 plus omega square into 0.16 square is the magnitude. Angle is minus 90 integral factor, one first order denominator factor. Angle is minus tan inverse of 0.33 omega, and first order denominator factor phase angle for another factor, that is first order denominator factor, it is minus tan inverse of 0.167 omega. Okay, so this is it. This is the phase angle of the given system. So this is it. So just write down phi is equal to this. Take phi is equal to this. Write it down for different omega values. You can determine phi. So write down this equation, phi value, phi equation. Okay, if you have written. So for write down this table for different omega values. I have assumed one omega is 0.5, 1, 3, 6, 10, 20. Right, determine the phase. From the above formula, just determine the phase phi, phase angle phi. So for 0.5, angle is minus 104. For 1, omega value 1, angle is minus 118. For omega value 3, angle is minus 161. You can write 161 as it is, or you can round it off to minus 160. It is not necessary to round it off to the nearby zero value. It's not compulsory. If you want, you can do it. So for 6 omega value 6, angle is minus 198. For omega value 10, angle is minus 222. For omega value 20, angle is minus 240. Okay, 244. So these are the uh, phi values and omega values. You can give some notations to them on the graph. So E, F, G, H, I, J. If you want, you can give them notations. Okay, for each and every point on the graph, you can give some notations. So have your some notations there. Just write down this table. And I have assumed one unit equal to 20 degrees on y-axis. So are you able to follow? Is there any issue? Just inform. Are you able to follow? Is there any issue? Inform. Okay then. So I hope you have written the omega and phase values. Now just locate the points, five phase values for each omega value on the graph. So these are the points. So for zero point 0.5 radians, what is it? 0.5. This is my 0.2, 0.3, 0.4, 0.5. This is my 0.5 radians. Sorry. This is 0.5. This is 0.5. So 0.2, 0.3, 0.4, 0.5. This is 0.5 for 0.5. What is the angle? Minus 104. So you can see here, this is my scale. So I have considered from minus 260 to minus 80, 20 degree difference. Okay. 1 unit equal to 20. No need to write twice. I have written twice here. So no need to write two times. So just write only one time. That is more than sufficient. I have written two times. So don't do that. So minus 104, which is minus 104. So look at this point. Next point is for 1. Omega equal to 1. This is 1. For omega equal to 1, angle is minus 118. So minus 118 degrees. Base angle is minus 118 degrees. Similarly for 3. So 3 means 2, 3. This is 3. So for 3, uh, angle is minus 160 I have assumed. So this is minus 160. Okay. Next 6. So this is 6. So for 6, omega equal to 6. Angle is minus 198. For omega equal to 10, okay, angle is minus 222, triple two. For omega equal to 20, so this is 20. 20, phase angle, phi value is minus 244, okay, minus 244. So these are the points. Look at them on the similar graph sheets as quickly as possible. Okay then, join the points. You will get this plot. This is our phase plot. This is magnitude plot. This is phase plot. Okay, now let us go to step number 3, determination of phase margin of uncompensated system. So let us assume phi gc, it is the phase of g of j omega at omega gc, and let us assume gamma, it is the phase margin of uncompensated system. Okay, so now we can determine phi gc. Okay, if we know omega gc, if we know omega gc, we can determine phi gc. So if we know omega gc, we can determine phi gc. So omega gc we already know. Omega gc is obtained at 0 decibels. When A is 0, you can determine the omega gc. So omega gc is obtained at A equal to 0. So let us go to the graph. Let us go to the graph. In the graph, so you can see A value is 0 here. A value is 0 here. From here, draw a dotted line. Draw a dotted line towards the magnitude plot. It is intersecting magnitude plot here. From here, draw a vertical line towards the x-axis. Wherever it intersects the x-axis, that is our omega gc. So while traveling from this magnitude plot towards the x-axis, this dotted line cuts the phase plot at some point. From there, draw a horizontal line towards the y-axis of your phase. Okay, so you will get phi gc is equal to minus 226 degrees. Okay, just observe it. You can see a dotted line here. I will take the laser from 0 point. Okay, draw a dotted line towards the magnitude plot. So this dotted line will intersect the magnitude plot. Horizontal dotted line will intersect the magnitude plot at some point. From there, draw a vertical line towards the x-axis. Wherever it intersects the x-axis, that is our omega gc value. Now, while traveling from this magnitude plot towards this x-axis, this dotted line cuts the phase plot at some point. From there, draw a horizontal line towards the y-axis of your phase. So wherever it intersects the y-axis, that is our phi gc. Phi gc is equal to minus 226 degrees. That's what you get from this Bode plot. Okay, so from the Bode plot, you have got phi gc is equal to minus 226. Okay, so let us go back. Just put the dotted lines and write down phi gc value in the graph. Okay, I hope you have completed. If you complete, you just mention the chat box so that I will come to know that you have completed and I can proceed. Now, let us go back now. So, what is this phi gc? Phi g is in the phase of g of j omega at omega gc. And what is gamma? It is the phase margin of uncompensated system. Okay. Now, from the Bode plot, for the uncompensated system, what did we get? Phi gc is minus 226 degrees. What is gamma formula? It is phase margin formula is 180 plus pi gc. So what is pi gc minus 226? Substitute in this formula. Gamma equal to 180 minus 226. So what did you get? If you simplify 180 minus 226, you will get gamma equal to minus 46 degrees. Gamma is equal to minus 46 degrees. Now this is the phase margin for uncompensated system. Okay, this is the phase margin for uncompensated system, and if you see your question in the question that you have already written in your notes, if you see the phase margin that they have asked is, okay, in the question, I'm going back to the question. In the question, they have asked that phase margin should be greater than, where is my cursor here? Phase margin should be greater than or equal to 35 degrees. Phase margin should be greater than or equal to 35 degrees. So what is the phase margin that we have got? Minus 46 degrees. Okay, so we need a compensator to compensate the, okay, to get the required phase margin, we need a compensator now. Okay, so how much phase margin did you get for uncompensated? Minus 46 degrees. But our requirement is greater than or equal to 35 degrees. So we need a compensator. So let us go to next step. So step number 4, choose a new phase margin of the compensated system. Let us choose a new phase margin for the compensated system. What is the desired phase margin? In the question they have mentioned desired 35 degrees. So let us assume gamma d is the desired phase margin, that is 35 degrees. Okay, gamma d is the desired phase margin, that is 35 degrees. So phase margin of compensated system, new phase margin gamma n is desired phase margin plus initial choice value. So initial choice value, let us assume initial choice value is some 5 degrees. Okay, so since the gain crossover frequency position will change from its actual position, so therefore we need an initial choice value. So let us assume initial choice value is 5 degrees. Desired, we already know, desired phase margin is 35 degrees. So new phase margin we have to determine. So new phase margin is equal to desired phase margin plus epsilon. So what is our desired 35 and initial choice is 5. So what is our new phase margin now? 40 degrees. So new phase margin for the compensated system, we have got 40 degrees. Okay. So this is it. Just write it down. So I hope you have written. Now let us go to step 5. Determine the new gain crossover frequency. So let us assume omega GCN is the new gain crossover frequency and phi GCN is the phase of G of J omega at omega GCN. Okay. So phi GCN is the phase of G of J omega at omega GCN. At omega GCN. So at omega GCN, so this is actually it is the subscript omega GCN. It is the subscript. So phase of G of J omega at omega GCN is phi GCN. Omega GCN new gain crossover frequency. Now what is our new gain margin? It is 180 plus phi GCN. Okay. So gamma is equal to 180 plus phi GCN. Okay. So what is phi GCN now? Phi GCN is gamma n minus 180. What is gamma n? Just now we have determined the previous step, that is 40. New phase margin is 40. So phi GCN is equal to 40 minus 180. So phi GCN is minus 140. Okay. So the phase at new gain crossover frequency is minus 140. So since we have phase at a new gain crossover frequency, we can determine the new gain crossover frequency for this phase. For this phase, we can determine omega GCL. Okay. So if you know phi GCL, you can determine omega GCL. So let us go to the Bode plot. Okay. So what is phi GCL? We have got minus 140. Okay. Minus 40 is our phi GCL. I will take laser. Phi GCN is minus 140. From there, draw a dotted line towards the phase plot. Okay, towards the phase plot. So wherever this dotted line intersects, this yellow color dotted line, what you can see, wherever it intersects the phase plot, from there, draw a vertical line towards x-axis. It will intersect x-axis at some point. That is omega GCN. So here my omega GCN is 1.8 radians per second. Okay. So phi GCN just now we have calculated theoretically. So phi GCN we have got minus 140 degrees. Phi GCN is minus 140. From there, draw a dotted line towards the phase plot. This green color is phase plot, blue color is magnitude plot. So draw a dotted line towards the phase plot. So wherever it intersects the phase plot, from there, draw a vertical line towards the x-axis. So wherever this dotted line intersects x-axis, that is our omega GCN. So what is our omega GCN here? It just wherever it intersects, that is 1.8. Okay. So locate that omega GCN and phi GCN in the graph quickly. I hope you have located. Okay. Now, how much is omega GCN? We have got 1.8 radians per second omega GCN from the graph. Now let us assume omega GCL. It is a gain crossover frequency of lag compensator. Omega GCL is the gain crossover frequency of lag compensator. Okay. And omega GCL should be value should be always greater than omega GCL. Lag compensator, gain process frequency lag compensator should be greater than, it should be such that its value should be greater than omega GCL. Omega GCL, how much did you get? 1.8 radians per second. You choose some value randomly, okay, which is greater than 1.8. You can choose any value greater than 1.8 on your own wish. Okay, on your own wish, you can choose some value greater than omega GCL. Here, I have chosen. So it's our desired value. It is not specified omega GCL value. You just calculate, you just get the omega GCL from the graph. After that, choose some value on your own for omega GCL. So omega GCL is 1.8. I have assumed omega GCL is 4 radians per second. Okay. So you choose some value for omega GCL. So I have assumed omega GCL is some 4 radians per second. Okay. So omega GCL, we are not going to calculate it from anywhere, or we won't get it from the graph. Simply, we have to determine omega GCN, and we must choose omega GCL such that omega GCL is greater than omega GCL. Okay, omega GCL is greater than omega GCL. Now let's go to step number 6. Determine the beta parameter of lag compensator. Determine the beta parameter of lag compensator. So from the Bode plot, okay, uh, let us determine the dB value, means magnitude A value for omega GCL. Omega GCL, what did we assume? We have assumed some value greater than omega GCN. So what is omega GCN value? 1.8, which we got from the graph. So, okay, so what is omega GCL? 4 radians. For this omega GCL, what is A value? Let us determine. For this omega GCL. So what is my omega GCL? This is it. See, omega GCL is 4. From 4 on x-axis, draw a dotted line. From this 4, I will erase it. Erase it. From this omega GCL value, which is 4, from this point, draw a dotted line towards the magnitude plot. Wherever it intersects the magnitude plot, from there, draw a horizontal line towards the x-axis of your, y-axis of your magnitude scale. Okay. So from the x-axis, draw a vertical line from omega value equal to 4. From there, draw a vertical line towards the magnitude plot. Wherever it intersects the magnitude plot, from there, draw a horizontal line towards the y-axis. Okay. So wherever this dotted line intersects the y-axis, that value is, you can see here, I have got 23 decibels. Okay, AGCL. That is our AGCL. For omega GCL, A value is 23 decibels. AGCL is 23 decibels. So just look at this on the graph. Draw it quickly. Okay then. Okay then. So AGCL is 23 decibels. Omega GCL is 4. So let us go back to our step number 6. So for omega GCL of 4, what is the A value? dB in magnitude. dB magnitude is 23. Okay. So A GCL is 23 decibels. So the formula we have to determine beta value. So formula to determine beta is A GCL is equal to 20 log beta. Okay. A GCL is equal to 20 log beta. So A GCL by 20 is equal to log beta, and beta is equal to 10 to the power of 23 by 20. Okay. AGCL value is 23, isn't it? So beta equal to 10 to the power of 23 by 20. You just solve it. Okay, just from this determine beta, you can easily determine. Beta value I have got 14. Just write it down. Beta value is 14. Okay, so whatever here equations are there, you can directly simplify. AGCL equal to 20 log beta. Determine beta. Beta you will get 14. I hope you have written. Okay. Now let's go to the next step. Step number 7. Step number 7. Determine the transfer function of lag compensator here. Determine the transfer function of lag compensator. Okay. So always remember 0 of lag compensator will be placed at a frequency 1/10 of omega GC. Okay. It will be always placed at a frequency 1/10 of omega GCL. So we already know formula for the lag compensated zero. What is the lag compensated zero formula? It is 1 by T. So ZC1 is equal to 1 by T1. That's equal to omega GCL by 10. Okay. So from this you just simplify and determine T1 value. T1 value you will get 2.5. So pole of the lag compensator formula is what? PC is equal to 1 by beta T. So here PC1 equal to 1 by beta T1. So 1 by beta value just now we have calculated in the previous step, that is 14. T1 value is 2.5. So 2.5 simplify it, you will get PC1 equal to 1 by 35. Just solve it, you will get some value. Okay, just write it down quickly. Okay then. I hope you have written the pole of lag compensator. Now let's go to the next step. Okay, actually, sorry, we have to determine the transfer function of lag compensator. We didn't determine the transfer function. So let us determine the transfer function of the lag compensator. So what is the formula for lag compensator? Transfer function of lag compensator, some GC1. Okay, GC1. I have written G1 here. You can write GC1 because compensator transfer function. You can write GC1. I have written only G1 of S. So is equal to beta into 1 plus S T1 by 1 plus S beta T1. So beta value and T1 value, we have the beta and T1 values. So substitute beta and T1 values. Okay. So if you substitute beta and T1 values, you will get GC1 or G1 of S is equal to 14 into 1 plus 2.5S by 1 plus 35S. So this is the transfer function of lag compensator. Now it is our lag lead compensator. So we also have to determine the transfer function of lead compensator. So let's go to step number 8. So determine the transfer function of lead compensator. So we know the relation between alpha and beta. We know alpha into beta equal to 1. So in theory, just now we already discussed. So alpha into beta is equal to 1 for lag lead compensator. So alpha is equal to 1 by beta. So if alpha is equal to 1 by beta, we know the beta value is 14. So 1 by 14, alpha value is what? 0.07. Alpha value is 0.07. Now, let us determine the magnitude A, dB magnitude. dB magnitude corresponding to omega n when frequency is okay. So when the phase lag or phase lead is maximum. Okay. So the frequency is omega m at that point. Okay. So at A at omega equal to omega m formula is 20 log magnitude is 20 log 1 by root alpha. Okay. So what is alpha value? 0.07. So minus 20 log 1 by root 0.07. Simplified, you will get minus 11.5 decibels. So what is A value? Minus 12 decibels. Okay. A value at omega equal to omega m is minus 12 decibels. Okay. So A value you have got minus 12 decibels. So now let us go to our uncompensated system. Just write it down. We will go to the graph later. Simply we have already got the transfer function of lag compensator. Now we want the transfer function of lead compensator. For that, we are assuming alpha is equal to, for lag lead, alpha is a relation between alpha and beta is what? Alpha and beta. Alpha into beta is equal to 1. So alpha is equal to 1 by beta. That condition we are implementing here. So we have got some value for alpha, and we know at omega equal to omega m, whether it is phase lag or phase lead. For phase lag, phase will be in the negative axis maximum, and for lead compensator on positive side or positive axis, it will be leading. Okay, maximum. Phase will be maximum or minimum. Negative maximum, I can say. Minimum means negative maximum. So phase will be either maximum or in the negative side maximum or minimum. So maximum or minimum at omega m. So A value at omega equal to omega m. Formula is this. Substitute alpha value. You have got minus 12 decibels. So I hope you have written. Let's go to the graph. So where is my graph? Graph. So this is my graph. This is minus 12. This light blue color line. I hope you are able to see. This is it. This is this line, my light blue. From here, draw a line towards the magnitude plot. Okay, from minus 12. So wherever it intersects, from there, draw a vertical line towards the x-axis. That is our omega m value. That is our omega m value. Okay, so write down the omega m value from the graph. Okay, so omega m value from the graph. So I will just check it. So omega m value is, this is 10, this is 20. So it is nearby to 20, approximately 17 or 18 radians per second, omega m value. So look at this on the graph. Look at this, minus 12. This is minus 12. Light blue color line. This light blue dotted line, you just carefully observe. From this, we can determine the omega m value. So for uncompensated system, so that is it, omega m. I have got 17 radians per second. Omega m is 17 radians per second. So now what is T2? Formula for T2 is 1 by omega m root alpha. Okay. So okay. So 1 by omega m root alpha. Omega m we have got from the graph, that is 17, and alpha is 0.07. You will get the T2 value. So for the transfer function of your lead compensator, T2 we have got 0.22, and alpha value is 0.07. Substitute that in G2 of S. This is the transfer function of lead compensator. Alpha into 1 plus S T2 by 1 plus S alpha T2. Okay. So this is it. Just substitute the values here. The formula, you will get G2 of S is equal to 0.07. 1 plus 0.22 S by 1 plus 0.0154. Write it down quickly. Okay, so I'll proceed. It's already late. Now step number 9. In step 9, determine the transfer function of lag lead compensator. So transfer function of lag lead compensator, Gc of s is equal to G1 of s into G2 of s. Just now we have determined G1 of s and G2 of s. So G1 of s is beta into 1 plus st1 by 1 plus s beta t1, and G2 of s is alpha into 1 plus st2 by 1 plus s alpha t2. So just write down whatever you have got earlier. So for G1 of s, so Gc of s is 14 into 1 plus 2.5s by 1 plus 35s into 0.07, 1 plus 0.22s by 1 plus 0.0154s. So just solve it. You will get Gc of s is equal to 1 plus 2.5 s into 1 plus 0.22s whole divided by 1 plus 35s into 1 plus 0.0154s. So just write it down as quickly as possible. So I will conclude within as quickly as possible. I will conclude. Okay. So this is the transfer function, compensator transfer function, when both lag and lead compensators together they are operating. So now we can what we can do is in step number 10 we can determine the open loop transfer function for the compensated system. So we have got a transfer function for the compensator. This is Gc of s. This is Gc of s, and this is G of s. This is G of s. Both are connected in series. The compensator and the plant. Okay, plant we can say open loop transfer function. They are connected in series. And this is our unity feedback. Okay, this is our unity feedback. So just draw this block diagram. So you just solve it. You just multiply these two terms, you will get the open loop transfer function. Multiply the gain values of these two, you will get the open loop transfer function. Okay. So now we have connected the compensator. Now we have connected the compensator to the open loop here. Therefore, we can call this system as the compensated system. Okay. So open loop transfer function for the compensated system, let us assume it as G naught of S. So G naught of S is equal to Gc of S into G of S. What is Gc of S? Just now it is there in the above diagram, and this is our G of S. Okay, Gc of S and G of S. Just simplify it, you will get G naught of S, compensated system transfer function. G naught of S is equal to 80 into 1 plus 2.5s into 1 plus 0.22s by s into 1 plus 35s into 1 plus 0.0154s into 1 plus 0.33s into 1 plus 0.167s. Okay. So I would ask you to write it down. If people just write it down later. So this is it. This is our open loop transfer function now. So for this transfer function, you can determine sinusoidal form of this transfer function, and you can plot the body plot for this compensated system. This is our compensated system transfer function. So for this, so you just go to step number 11. Next step, Bode plot of compensated system. What we have to do is replace S by J omega in the above equation. You will get this. Okay, G naught of J omega equal to 80 into 1 plus 2.5 J omega into 1 plus 0.22 j omega by j omega into 1 plus 35 j omega into 1 plus 0.0154 j omega into 1 plus 0.33 j omega into 1 plus 0.167 j omega. Okay, this is what you will get. This is it. This is the sinusoidal transfer function. So if you know the sinusoidal transfer function, you can go for magnitude plot. You can go for magnitude plot. So magnitude plot. Magnitude plot. How many corner frequencies can we determine? So see here. How many factors are there? One integral factor is there. First order numerator factors. Two first order numerator factors are there. Okay, and first order denominator factors total 1, 2, 3, and 4. Total 4 first order denominator factors are there. So one integral factor, two first order numerator factors, and 4 first order denominator factors are there. So how many corner frequencies do you get? 4 plus 2. Total 6 corner frequencies you will get. So omega C1, omega C2, omega C3, omega C4, omega C5, and omega C6. So you can see here, what are the T values? You just see here. Here for this factor, T value is 2.5. So 1 by 2.5, 1 divided by 2.5, 1 corner frequency, 1 divided by 0.22, another corner frequency. This is another corner frequency. This is one corner frequency, and 1 divided by 35. 1 divided by 35, one corner frequency. 1 divided by 0.054, another corner frequency. 1 divided by 0.33 is another corner frequency. 1 divided by 0.167 is another corner frequency. Okay. So T values are 2.5, 0.22, 35, 0.0154, 0.33, and 0.167. These are all the T values. So 1 by T is our corner frequency formula. So substitute it and you will get this. So just take a minute and write it down. Omega C1, omega C2, omega C3, omega C4, omega C5, and omega C6. Okay, so now let us go to the magnitude table and let us go to the magnitude table and write down all the basic factors. Integral factor and all the, this is our first order denominator, first order numerator, first order denominator, first order numerator, first order denominator, and first order numerator. The sequence, in which sequence you have to write, you will come to know depending on the corner frequencies. Okay, whichever corner, whosever corner frequency is least. So here you have got 0.03 is the least, at highest you have got 65. So you must, whichever to whichever factor you have got the least corner frequency, you write for that factor first. Later, greater than this is this. So write that factor next. And greater than this is this. So you write the next factor next, and so on in increasing order. Okay, from lowest corner frequency to highest corner frequency. Write down all the factors in order and write their slope values. For integral factor it is -20. For first order denominator factor -20. For first order numerator factor +20. First order denominator -20. First order numerator +20. First order denominator, first order denominator. After that, as I have already explained, change in the slopes. Okay, I have explained it in the earlier in the beginning of this numerical problem. So write down the slope of first factor in the next row and add it with the slope of that particular factor. You will get -20, -20, 40. Send 40 here. Added with +20, -40, +20, you will get -20. And send this -20 here. minus 20 plus minus 20, you will get minus 40. Send this minus 40 here and add it with plus 20. You will get minus 20. Send this minus 20 here, add it with minus 20. You will get minus 40. Send minus 40 here, add it with minus 20. You will get minus 60. Okay. So these are all the changes, change in slope values. Okay. Change in slope values. These are the change in slope values. So you can write it down later. It's already late. No need to write now. Just look at this. I will try to conclude as quickly as possible. Okay. Now let us choose lower frequency and higher frequency. So our least corner frequency was omega C1, highest corner frequency was omega C6. So least corner frequency is 0.03, 0.03. Highest corner frequency, so whatever corner frequency that we have got, that was 65. So lowest was 0.03, highest was 65. So omega L should be less than omega L should be less than 0.03. So omega L I have chosen low frequency, low frequency 0.01. Highest frequency I have chosen 80. Okay, omega L low frequency omega L 0.01 radians per second, high frequency omega H that is 80 radians per second I have chosen. Now determine A naught. A naught equal to magnitude of G naught of J omega in decibels. So let us determine A naught for all these frequencies from omega L, omega C1, omega C2, omega C3, omega C4, C5, C6 and omega H. So when omega equal to omega L, what is A naught? 20 log 80 by omega L. Omega L value is what? 0.01. Substitute that here and solve it, you will get 78 decibels. Similarly, for omega equal to omega C1, A naught is 20 log 80 by omega. So what is omega value? Omega C1 value is 0.03. Substitute that, solve it, you will get 68.5 decibels. You can leave it as it is or round it to 68 or 69 decibels. I have rounded it to 68 decibels. Now consider omega equal to omega C2, sorry. So A naught is, since after first corner frequency, formula will change. This omega C1 is the first corner frequency. After that, formula will change. A naught is equal to slope from omega C1 to C2 into log omega C2 by C1 plus A at omega equal to omega C1. So just substitute all the values. Substitute all the values. A naught you will get 23 decibels. Similarly, omega equal to omega C3, A naught equal to slope from omega C2 to omega C3 log into log omega C3 by omega C2 plus A at omega equal to omega C2. Substitute all the values, you will get A naught equal to 5 decibels. Similarly, for omega equal to omega C4, A naught is minus 2 decibels. Okay. Similarly, for omega equal to omega C5, A naught is minus 4 decibels. Same formula, I will not repeat the same again and again. For omega equal to omega C6, A naught value is minus 45 decibels. Next, for omega equal to omega H, A naught is minus 50 decibels. Okay. So now you can plot the graph. We have different omega values and A naught values. You can plot the magnitude plot. So before going for magnitude plot, okay, you can plot the magnitude plot. This is it. These are my points. Okay, this is the magnitude plot for the compensated. This is the magnitude plot for the compensated system. Sorry, yeah. Okay. And this is the magnitude plot for the uncompensated system. Earlier we got this plot. Now for the whatever points you have got, this is the magnitude plot that you will get. So similarly, let us go to the phase plot. Phase plot, phi naught. You will get tan inverse of 2.5 omega plus tan inverse of 0.22 omega minus 90 minus tan inverse of 35 omega minus tan inverse of 0.0154 omega minus tan inverse of 0.33 omega minus tan inverse of 0.167 omega. Okay, so directly you can write it down from the sinusoidal transfer function. You can directly write it down. So if you want, I can show you the sinusoidal transfer function, and from that I can tell you how to write it down. So this is it. See here. Okay. So tan inverse of 2.5 omega, tan inverse of 0.22 omega, minus tan inverse of integral factor is there. Minus tan inverse of, sorry, for integral factor minus 90 degree, minus tan inverse of 35, minus tan inverse of 0.015 omega, minus tan inverse of 0.33 omega, minus tan inverse of 0.167 omega. Okay, so which are factors are there in the denominator? For them, tan inverse of t values, or t, actually it is not t, it is b by a. This value 0.33 by 1 you should write. Okay, whichever terms are in the numerator, 2.5 by 1 to 0.22 by 1 you should write. For integral factor, angle is minus 90 degrees. So that is it. That's what I have written here. Angles. You can compare it with the sinusoidal transfer function. These are the angles. So now for different omega values, you can determine phi naught. For different omega values, determine phi naught. Okay. So this is my table. Okay. So where is it? Yeah. For omega 0.01, this is 5. For 0.03, for 0.1, 0.4, 4, 10, 65, and 80. These are my angles, 5 values for different omega values. So I have got this. These are the 5 values. Okay. Now look at all the points on the graph. Okay. Look at all the points on the graph. These are my points and join them. Okay. So this is what I have got. Phase plot of compensated system. This is the phase plot of compensated system. This is the magnitude plot of compensated system that I have got. Okay. So you can do it for as it is similar to uncompensated system. So you can do it. Just I'm about to conclude within 1 or 2 minutes. I will complete this. So now let us consider phi GC naught is the phase of G naught of j omega at gain crossover frequency at omega GC naught. Okay, phi GC naught is the phase at omega GC naught. I have not written here omega GC naught. GC. Okay, so phi GC naught is the phase of G naught of j omega at uh, omega GC naught, and let us assume gamma naught is the phase margin of compensated system. Okay, gamma naught is the phase margin of compensated system. Okay, so from the Bode plot, of compensated system, we know omega GC naught is obtained at A equal to 0 decibels. Omega GC naught is obtained at A is equal to 0 decibels. So let us go to our plot. Okay, so from I have not done here. Yeah, so you just see here, this is 0 decibels. From here, draw a dotted line. Draw a dotted line, purple line. You just observe. Draw a dotted line towards the new, new means magnitude compensated system magnitude plot. Okay, magnitude plot, compensated system magnitude plot. So just draw a dotted line from 0 decibels. Wherever it intersects the magnitude plot of compensated system, from there draw a vertical line towards x-axis That is our omega GC naught. Okay, that is our omega GC naught. So while traveling from this magnitude plot of compensated system, okay, so this dotted line, purple dotted line, what you can see, it cuts the phase plot of compensated system. This is our phase plot of compensated system. It cuts the phase plot of compensated system at this point, isn't it? From there, draw a dotted line, horizontal line towards the y-axis of phase. You will get 5 GC naught. I have got it is minus 144 degrees. 5 GC naught is minus 144 degrees. Okay, so how much pi GC naught did I get? Minus 1.4 degrees. So omega GC is always obtained at where? It is always obtained at 0 decibels. Okay, A in 0 decibels. When A is 0 decibels, you'll get the omega GC value. So now let us go to our PPT. So what is pi GC naught now? Minus 144 degrees. Okay. Now what is phase margin of the compensated system? 180 plus 5 GC naught. So 180, what is 5 GC naught minus 144? So it is 180 minus 144, you have got 36 degrees. Okay. So phase margin of compensated system is 36 degrees. So in our question, they have told us this phase margin should be greater than or equal to 35 degrees. So 36 degrees is greater than 35 degrees. Therefore, phase margin of this phase margin is satisfactory, hence this design is acceptable. Okay, this phase margin is satisfactory and the design is acceptable. So this is it. I hope you are able to follow. If you are able to follow, just mention in the chat box whether you are able to follow or not. Whether you are able to follow or not, just mention in the chat box. I will once again show the overall plot. This is our overall plot. Magnitude plot of uncompensated, phase plot of uncompensated, magnitude plot of compensated, phase plot of uncompensated. If you have understood, just click on like button so that this video will be available for more and more people, outside people. If you click on the like button, more people can go through this video later. Okay, if you have understood the concept, you can click on like button. Okay then, thank you for joining the class.